My name is Matthias Mayr. I'm with the University of the Federal Armed Forces in Munich, Germany. We've been a Trilinos user for 20 years. So I'm gonna try, and I think I spent 15 of those 20 years, I was part of the project. So I'm gonna try to share some of, well, first of all, explain what our code does, how we benefit from Trilinos, what the challenges are that we face, how we try to get a handle on them, and how we actually also manage to pull off at least some co-development of both frameworks. So I'll not dive into Trilinos. We've spent an entire session on what it is. Let me rather go and explain what 4C is. So 4C is it stands for Comprehensive Computational Community Code, so what the 4 times the letter C is. And in the end, it's a comprehensive multiphysics simulation framework. So we really focus on doing computational research in multiphysics systems. We want to run stuff in parallel, and we want to really cover a very broad range of multiphysics systems. And all this is, and I'm going to focus on that, enabled by using Trilinos. Our guiding principle is that we want to use software as a tool to implement numerical methods and to develop numerical methods, but always with the strong focus on answering research questions in coupled multiphysics systems. And here's some exemplary areas. So we do basic science, like developing numerical methods and algorithms. We look into material modeling, and then, for example, biopolymerimetrics, like a biophysics application. We all come from engineering departments, so engineering engineering disciplines, aerospace, mechanical, civil, are our core competence. And we do also do a lot of work in biomedical simulation. There in particular respiratory system, cardiovascular system, and all those listed here. At the bottom you see just a variety of pictures that kind of highlight whatever we want to do, and that hopefully gives you an impression of the width and of the areas of application that we have. In 4C itself, of course, we start off with some single field implementation, solid mechanics, structural mechanics, fluid dynamics, and so on. But then the core is really coupled multiphysics. So we have a series of ready-to-use coupling algorithms tailored to particular physics. We're going to start with stuff like fluid beam interaction, fluid solid interaction. SSI stands for solid scattera interaction, solid scattera thermo interaction, and TSI is thermal solid interaction. And there are other acronyms with more than 3 letters that I don't remember, so I just abbreviate them with a couple of dots. So, and as you see in this word cloud thing on the right, these are all the, let's call it modules from our source code. Just use those words and create this word cloud, and you see that the interaction is really kind of the core. It's the word that occurs the most. So this interaction between these individual fields, that's what we're interested in. And of course, in order to do numerical simulation there, we need to do some numerical methods. We mostly do finite elements. We do have some isogeometric capabilities and cut-fem. So your cut finite element techniques. We do have some particle algorithms. And yeah, we do time integration, nonlinear solvers, and of course linear solvers and preconditioners. So let me shift a bit more towards the technical side of the code. So as I mentioned, we use Trilinos mostly for sparse linear algebra, nonlinear solvers, and linear solvers and preconditioners. So we don't go what the previous talk said, if you're fully in love with Trilinos, well, I am, but technically we can't pull off the Panzer thing. So, but I hope you use a decent amount that's helpful for us. So for C uses Trilinos itself, it is fully implemented in C++. So far, we are, in terms of parallelization, limited to MPI. We're working on moving towards tPetra so that we have the option of doing some Cocos things, but that's work in progress. Since a couple of months, we are actually open source on GitHub, so you can find us there. Yeah, and I also want to highlight this. It's not only developed by our group. So we have a couple of partners so far, mostly limited to other institutes in Germany, and we hope that people join over the time. Yeah, most importantly, and maybe relevant for this community here is some of the tools that we use. So we use Trilinos, as I mentioned above, ArborX. Some of you might know something that we use, well, apparently for search algorithms. And then some of the rather classical stuff, how to, well, build and maintain and ship code. So you know a little bit about what for C is. Now the question is, why do we go for Trilinos? We believe that our expertise and core interest in our research is numerical modeling of these coupled multiphysics systems. And yes, although we do develop software, we don't consider ourselves to be software engineers, and we don't want to do software just for the sake of doing the most awesome, the best documented, or the most performant software. So for us, it's rather a tool to answer actual research questions on multiphysics. So, and here is where for us the benefits of Trilinos come in. We do, because we consider it to be a well-matured scientific software library that brings certain aspects to the table that we just want to leverage. First of all, it's suitable for finite element discretization of PDEs. We heavily rely on sparse linear algebra implementations in Trilinos, and we use and develop and contribute to those iterative solvers and preconditioners in Trilinos. For us, I put parallelism for free here. So basically, we don't have to, we use distributed linear algebra just through ePetra, or hopefully soon through tPetra. Don't have to think about all these types of things. And we hope that we can run on modern computing architectures without having to, well, dive into the topic too much. We found that we get a certain amount of scalability out of the box, so we can just focus on the physics, and we still can run on a decent number of cores. I'll show results later. And of course, we get some stream of updates and improvements just by keeping up with the changes that happen in Trilinos anyways. Some part of history, how we use Trilinos. So it all started in 2005 by Michael Chi coming back from Trilinos, from Sandia, and bringing Trilinos with him. And so that's when he started this code based on ePetra for sparse linear algebra, then some linear solvers and preconditioners, mostly basically Amisos, Aztec, IFPEC, and ML, and then some utility packages. And then over the last 10, 15 years, we added new packages to our stack, mostly Nox, and then Intrepid, and Tico. And so we're also now recently updated, or in this move towards tPetra, updated those packages. So switching from Amisos to Amisos 2, ML to Mulo, Aztec to Belos, and so on. And so this is completed, and the stuff in the upper box. What we're currently focusing on, and we're not gonna make the September deadline, but hopefully we don't miss it by too much, is we're really focusing on getting this ePetra, tPetra transition done, along with IFPEG to IFPEG2. And we are thinking about integrating Stratimicos just to ease our interfacing with linear solvers. So this is a current work in progress. So how do we use Trilinos, or how do we integrate it into our code base? So I picked out three aspects. One is that we currently is wrappers. So currently we use a mix of wrappers and direct use, meaning that, for example, we used to have a wrapper for all the sparse matrices, but for whatever reason, we used the ePetra vectors directly scattered all across the code base. So we are actively pushing all ePetra stuff for all Trilinos occurrences to distinct interface classes, so that we, on the one hand, can find out what we actually use, and then hopefully that in the end, that we can control the interface and expose certain features to the user, and maybe also, well, add some convenience to those interfaces in case that somebody finds a direct Trilinos interface not so convenient. And mostly we hope that this helps us in transitioning to tPetra, so that you only have to switch ePetra for tPetra at a limited number of places. In terms of updating Trilinos or keeping up with changes in Trilinos, we use an internal versioning scheme. So I know Trilinos does releases on a sometimes regular basis. We don't rely on that for two reasons. One is that if we feel we need an update, we just want to do it, and then we use our own internal versioning scheme to basically map a certain Git hash from the Trilinos repository to that version number, and that allows us to pull an update whenever we want. Most frequently, whenever we contribute something to Trilinos, of course, we want to have it back in our code as soon as possible. So that basically means we then pull an update and create a new internal Trilinos version for us. And it also allows us to build against several of these internal versions, and so every developer can decide for themselves whether they want to do the update or not. And what we found helpful in that regard is that we also run in our CI like a forward-looking CI pipeline, meaning that once a week we just pull the most recent develop and build and see what happens. And so that at least we have a chance to fix issues along the way and don't let them pile up. In terms of installing or providing Trilinos to the code, we don't do the spec thing for Trilinos, so we use spec to basically install everything else that we need, all the TPLs and stuff like that. And then we manually build and install Trilinos and then use standard CMake integration into our code base. And yeah, so I didn't count the options. Apparently it's 250, what Sam told us. So we do have the scripts for our packages to configure them. So we are comfortable with building Trilinos manually. And especially we are not comfortable with doing it through this one huge spec interface. So that's mostly the reason why we still stick to the manual Trilinos build.
Is the reason because you're also developing Trilinos, or is there another reason?
It's just if you type spec in for Trilinos, it's overwhelming. Okay. That's the main reason. And then we have some people who develop Trilinos and they want to compile it manually. And there's this spec develop mode, I think, but so we haven't looked into that. For those who just use Trilinos, a spec installation would be fine, but there's just this overwhelming large number of variants in the spec package. That's the reason, yeah. So we work with Trilinos and it works very well, but there are some challenges in using it and also in developing it. So what became apparent also in the previous talk is about the CMake and trib adoptions. They can be overwhelming, especially for new users. And in our case, it's a university setting. That means new PhD students who might never have seen CMake at all and might never have used a library of such scale. So this is just a challenge. We hope that we can make it usable for them. So far, everybody got it to run. And we also fix it mostly by providing centralized installations that they just link against. Something that also has come up today is, well, documentation and tutorials are somehow, well, there's room for improvement. So, yeah, and sometimes there is documentation, but it's apparent that it's outdated. And in terms of contributing to Trilinos, but that also has been discussed in the previous talk. I mean, it's really, really hard to do something if you can't look at the results. And this pre-inspection thing is also, let's say, annoying. And I understand, for both cases, I understand the reason why it is as it is, but I still want to share the feedback. On the plus side, I mean, we are grateful for all the packages and the functionality that we can use and that we can leverage. That we are, what I like, and that we've seen it in the past with some smaller changes, and we now see it with the ePetra deprecation, that there is some structured process to do that, and we just have to follow that and try to keep up. And then the last 2 points, well, they address all the challenges that are listed above. If we reach out to somebody on GitHub, we get well, people are very helpful, and I'm really grateful for that, and I appreciate it. No matter if I do it, where I do know some more people in person, or whether one of my colleagues does it, who's just some unknown guy on GitHub. So this is really nice, and I want to also, well, play that back basically to the Sundians here in the room. This helps us in order to overcome some of the challenges above. What I personally like very much is that over the recent years, we actually came into a mode where we can somehow co-develop Trilinos in our own code. And this is mostly driven by some characteristic of those multiphysics systems that we're interested in. So mostly we end up with some sort of block matrices where properties vary across the field. So we somehow need to account for the blocks and do different things for each block. And of course, all these systems are usually pretty ill-conditioned. So on the co-development side, we do use and also contribute to certain parts in the block preconditioning area. For TICO, we're mostly users for now. For MULO, we're actively contributing also techniques how to deal with block matrices, and then algebraic multigrid methods in MULO in general. And then I pointed out some like parts in Trilinos where I think that and I'm kind of proud of that they conceptually originated from our code. And this is like all this ex-Petra blocked stuff that Tobias Wiesner put in, the idea of the ePetra map extractor. That's basically a one-on-one copy. And then also some MULO factories that we actually were able to contribute. And I don't know how I'm on time. at time. And then I highlight just one example. So this is the embedding of fibers into solids. It's our most recent work where we use TICO and MULO both. And where we basically do an approximate block LU preconditioner tailored to the specifics of this 2x2 block system. It has some penalty parameters in every block, so we don't have diagonal dominance. We lose also block diagonal dominance, but still you can see the weak scaling results in the bottom right diagram. So the number of iterations is perfectly flat at something like 13. And then for multigrid setup time and GMRS solve time, we get decently flat lines with a similar observation that Jonathan made, that setup is usually more expensive than the solve time. With that, I think I showed what we benefit from in Trilinos, what we find challenging, how we still are able to work with it. And then I acknowledge funding. Thank you for listening, and thank you for the help that you provide us in doing whatever we want to do. Thanks.
We probably have time for one quick question while Malachi gets set up. Michael?
So you said you're in the process of port to T Petra. How close do you think you're to running on GPUs? Like, do you have architecture is going to be more right?
So we do have a GPU. We're currently, we bought some hardware and it's currently being set up. I'm not sure how close we are to actually running on that because I think that we still need 6 to 9 months, maybe 12 months to actually make the final switch to T Petra. And we don't have staff yet who's particularly interested in looking into GPU computing. So, yeah.
I'd just be very interested when the teams start collaborating on that space. It'd be another user.
I mean, for us, I think the main advantage there would be that I don't see us anytime soon to rewrite our own finite element assembly using Cocosy stuff. But I see the benefit that we can hopefully offload some of the Trilinos internal calculations to some accelerators.
The TICO stuff,
For example. Yeah.